Good morning, students. Today we will discuss a new topic, that is plane wave reflection and dispersion, in which we have taken two mediums, medium 1 and medium 2. This is the boundary of these two mediums. When a plane wave propagates from one medium, it meets a different medium, it is partially reflected back and partially transmitted to the another medium. Okay, so today we will study the effect of the dispersive medium on a wave. As wave propagates, some of its parameter changes, and due to that, these parameters, for example dispersion, attenuation and some more, must be evaluated when establishing the allowable transmission. So regarding that, let us evaluate the signal when it is transmitting from one medium to the another medium. Let us start the reflection of uniform wave, means plane wave, at normal incidence. Okay, when waves come to the boundary at normal position, that is perpendicular to the boundary surface. So for that purpose, let us consider the boundary. It is considered as, for simplicity, in xy plane, that is z is equal to 0, and wave is propagating in positive z direction, the propagation direction of the wave, and this is considered as medium 1, this is considered as medium 2, these two are different mediums, so accordingly it will have permeability mu1, epsilon 1 permittivity, and conductivity sigma 1. Similarly, it will have mu2, E2 and sigma 2. You can say omega 1 and omega 2 as well. Now consider that wave is propagating in z direction, then electric field and magnetic field component will be orthogonal to that, and next assumption we can do, the E component is in the direction of x. It can be in the direction of x and y, we can assume any of these two. Here we are assuming that it is in the direction of x. So y will be in the direction of h will be in the direction of y, and the propagation will be in the direction of z, which we have assumed already. The wave is propagating in the z direction, so incident wave is propagating in the az direction, positive z direction. Electric field component is in the direction of, EI indicates for incident wave, in the direction of x, and H component will be upward. So it is HI. These are the components, it will be in the direction of AY. These are the components of the incident wave, propagation in the Z direction, positive Z direction, and the electric field component is in the direction of AX, it is assumed. Then the magnetic field component of incident wave will be in the upward direction, that is in the direction of AY. At the boundary, when it strikes, part of it is reflected back. When it is reflected back, the propagation will be in the minus z direction, and when wave is propagating in the minus z direction, and we have assumed that the electric field component does not change its direction, then it is still assumed in the direction of x, reflected, okay, all are vector. it is still in the direction of AX. Then following the cross rule, if AP we know, either we can say direct AZ is equal to AE cross AH. If this direction is fixed and this is minus, then it must be minus. Okay, so if the for case of reflection it is minus Z direction, then AE reflected cross minus AH reflected should be there, and if it is minus, then it is going downward. Okay, it is in the direction of minus AY. So this is incident wave. The electric and magnetic field components are here. This is the reflected wave. Part of it has reflected and electric and magnetic field component in these directions, and the transmitted part will be in the direction of plus Z. Okay, and it will follow the same as it is here. Electric field is considered in the same direction, transmitted in this same direction, and magnetic field component will be coming upward. So H transmitted in the direction of AY. So these are the distribution of the electric and magnetic field component when it is changing from one medium to another medium. Once we know these, then we will try to find the relationship between incident and the reflected and transmitted wave. Now let us consider incident electromagnetic wave in medium 1. Incident electromagnetic wave, it is considered in medium 1. When it is, and we know EIZT, we know formula of this, we are familiar with this very well. Alpha Z when propagation is in plus Z direction, cos omega t minus beta Z propagation direction in the direction of AX. If we suppress the time factor and in phasor form if we write, then this equation in phasor form can be written as EIS will be equal to the E incident maximum value and e to the power minus propagation constant will be there at the place of alpha in the medium 1 propagation direction AX in phasor form. Okay, and if we have E component in phasor form, it has intrinsic impedance 1 and 2. Then H component can be written as magnetic field component of incident wave can be written as E. We know the simple formula, just I want to skip one step, that's why I have written E. That is HI incident, H incident maximum value e to the power minus gamma 1 Z in the direction of AY. And we know that impedance can be written as EI divided by H maximum value. From here, then we can write magnetic field component as 1. Okay, and if we put this in this equation, then we can write the magnetic field component in phasor form E incident electric field component divided by impedance e to the power minus propagation constant in the direction of positive Z AY. So from here we have equation 1, equation 2. These two are, we can say, final equations for further reference. Now this is regarding incident wave. Similarly, we can write for a reflected wave. Now, at this point, it is time to concentrate. Again, it will be medium 1 as reflection is back to same medium, and in that case, electric field component will be reflected in z direction, will be maximum value e to the power minus gamma z ax. This is the previous one. There should be modification in the propagation direction. It is propagating in minus z direction, so minus z here, it will give us like this. Now, this is the correct value now of the electric field component when it is reflected back in the same medium. And now, due to the propagation of the direction in opposite to the previous one, it is plus gamma z. And similarly, magnetic field component of the reflected wave will be in phasor form, E reflected divided by medium is same, so gamma 1 z ay. Okay. So, in this way, we have 4 final equations for further reference. Now, incident, reflected, hope it is okay. Why it is positive here? Incident, reflected. Now, the third one is transmitted wave. And in this case, medium will change. So, some changes also will be there in these equations. If medium is changing, then see where the change reflects. We can say ET transmitted wave will be ET naught e to the power. What will be this value? Propagation is in plus z direction. When the propagation is plus z direction, then it will follow this. And as medium is changing, gamma 1 will be here, gamma 2 will be here. So, it will be gamma 2 z in the direction of ax, as it is assumed in the beginning that the direction of electric field component remains same in both the mediums. Okay. Now, H component of the transmitted wave can be written as E transmitted divided by impedance 2 e to the power. It is following completely the incident wave in different manner except the material. So, it will be minus gamma 2 z in the direction of ay. It will follow exactly same. Now, in this way, we have 6 equations. Now, at the boundary, electric field and magnetic field will be, for example, this is the boundary. It is assumed that the surface is lying at z is equal to 0 and it is source free. In that case, the incident, or we can say the tangential component of electric field in medium 1 will be equal to the tangential component in medium 2 when it is lying at the bound D. Okay, so tangential component of electric field at the bound D will be equal, E1t will be equal to the E2t when it is lying at the bound D, that is at z is equal to 0. Similarly, when it is source free, there is no charge at all, then in that case H1t will be considered equal to the S2t. We can consider this, and if it is considered, in that case E1t we can find it combines the incident and reflected wave. So E1t can have E incident wave plus E reflected wave at the bound D. And if we will write at the bound D z is equal to 0, in that case at z is equal to 0, it will be equal to the, at z is equal to 0, it will be Ei naught plus Er naught from here and from here. That will be the tangential component at the boundary of electric field component. So we can say this is equation number 7. Similarly, E2t can be written as, from here in the for transmitted wave, Et is, and when z is equal to 0, it will be E transmitted naught. Okay, so in this way we have the Et1 and E2t. So as it is equal, from there we can say E T naught will be equal to the E I naught plus E reflected naught. So in this way we have one final equation for further study. We can name it equation number 9. Similarly, we can relate a magnetic field component, that is H1t will be equal to the H2t. So H1t will be the magnetic field component in medium 1, that is the incident wave and reflected wave. So E incident wave divided by medium 1. From here we can say when it is equal to the, at the boundary z is equal to 0, then we can write the Ei naught by eta 1, and as incident wave and reflected wave both have opposite direction of magnetic field component, so there will be minus E minus at naught it will be Er, it is minus Ay should be here. So due to this minus will be here, E reflected divided by medium 1. So the magnetic field component at the surface, tangential component is written here. This is equation 10. Similarly, the transmitted case, it can be H2t, that will be equal to the z is equal to 0, it will be in the direction of Ay. So when it is will be 0, it can be written as E t transmitted naught divided by medium 2, in the direct, it is named as equation number 11. As it is said, H1t is equal to H2t. From there we can write E T naught divided by 2, 11 and 10 can be equated. From there, incident divided by medium 1, reflected divided by medium 1. So we have this. This is another final equation for further study. This is equation number 12. So from equation numbers 9 and 12, we will try to find the relationships between incident, reflected and transmitted wave. Now there are two terms that is very important to know at this stage, that is a reflection coefficient of electromagnetic wave and transmission coefficient of electromagnetic wave. So let us start from a reflection coefficient of electromagnetic wave. A reflection coefficient means wave is coming and part of it is reflected. So from there, the ratio of reflected electric field component of reflected wave divided by the incident wave is termed as the reflection coefficient of electric field component of the electromagnetic wave. And to find the reflection coefficient, that is the ratio between R and I, reflected and incident, so transmission component will be eliminated. To eliminate that, let us multiply the equation number 12 from eta 2, and if we multiply from eta 2, then and we will subtract, then this term will be removed. So multiply equation number 12 by the impedance of the medium 2. So for that purpose, after that it will get eta 2 divided by eta 1 incident minus eta 2 by eta 1 reflected. This is equation number 13 now, and equation number 9 can be written as Et naught. From here we will write as it is, incident plus reflected. Now it is written. Now if we will subtract, then we will get cancelled out. We can cancel out these two. This will be eta 1 minus 1 Ei naught minus eta 2 plus 1 Er naught. When we will further simplify this to get Er divided by Ei, then it will be Er divided by Ei, it will be eta 2 divided by eta 1 minus 1 divided by eta 1 plus 1. Just this divided by this, it will be in the denominator, it will be equal to, okay. So further simplification will give us divided by eta 2 plus eta 1 divided by eta 1. It will be cancelled out, and the final answer will be impedance 2, impedance 1. This will be our final answer. So from here we can say the reflection coefficient is eta 2 divided by eta 2 minus eta 1 divided by eta 2 plus eta 1. Okay. Now let us try to find the transmission coefficient. So this is final finding that we should remember. Now the next is transmission coefficient. For that purpose, the definition that is given for transmission coefficient is E component of transmission wave divided by incident wave is named as transmission coefficient of electromagnetic field of component E. And if this is to be derived, for that purpose what we can do, we have to find the relationship between E T naught divided by E I naught. So E R naught should not be there, and for that purpose multiply this from eta 1, eta 1, eta 1. So if we will do that, either we can take this term here, then 12 equation can be modified as eta 1 divided by eta 2 E transmitted component E I naught minus E R naught, and ninth equation can be written as it is E T naught is equal to E I naught plus E reflected, and if we will add these two, then we will get 2 E I naught eta 2 plus 1 E T naught, and the ratio that we require to find is transmitted divided by incident component of electric field. So for that it can be E T naught divided by E I naught will be 2 divided by from here. So this is the final form that we have for transmission coefficient of electromagnetic wave. If we know the amplitude of the incident wave and we know the coefficient, then we can find the transmitted wave amplitude easily. In all these studies, we have assumed that the electric field direction remains same in both the medium. It may be also possible that the electric, at the place of electric field, the magnetic field component will remain same in both the medium, because that is based on our assumption, and electric field component will change accordingly. So in that case the calculation will change little bit, and for that purpose there will be little bit modifications on the basis of their direction.